this video, we're going to discuss molecular geometry. So first, what is molecular geometry? Well, basically, molecular geometry is the three-dimensional arrangements of atoms in a molecule, or basically the shape of a molecule. Understanding the shapes of molecules is very important because the shape of a molecule determines a lot of its properties, how reactive it is, its polarity, whether it exists as a solid, liquid, or gas, color, magnetism, and biological activity. Let me give you one example of why the shape of a molecule is important. Um, Enzymes are proteins in our bodies and other living things that speed up or catalyze chemical reactions. So enzymes are critical for life. Drugs generally are small molecules that can bind to an enzyme and cause it to no longer function. So that basically it inhibits the enzyme's activity. Um, Antibiotics bind to enzymes in bacteria. So for example, here, the picture that you see on the screen here, this large region here represents an enzyme in a bacteria. The molecule here is an antibiotic. This antibiotic binds to the enzyme, and when it binds, it prevents the enzyme from carrying out its normal function. When this enzyme can't function normally, the bacteria will die. So antibiotics, the shape of these antibiotics molecules is very important to their function. If the shape of the antibiotic molecule is altered just a little bit, it no longer functions and therefore won't effectively inhibit the bacterial activity and cause the bacteria to die. So this is one example of why molecular shapes are important. When we are determining molecular shapes, we use something called the Valence-Shell Electron-Pair Repulsion model, or VSEPR model. Essentially, the VSEPR model looks at the central atom in a molecule and studies the bonds and lone pairs that are around that central atom. The bonds and lone pairs are essentially regions of negative charge because they're electrons, and these bonds and lone pairs, since they're negative, they're going to repel each other and they're going to try to position themselves as far apart from each other as possible. It's this repulsion between the bonds that gives the molecule its three-dimensional shape. So let me give you an illustration of this using methane. Here we have the dot structure of methane. We have a carbon, which is our central atom, with 4 bonds around the central atom. Now these bonds, of course, are regions of negative charge because they are shared pairs of electrons. These bonds want to position themselves as far apart as possible. So if the bonds were to all be pointed down, there would be a strong repulsive force because all of these electrons are too close to each other. So this would not be a very effective position for the bonds in methane. That would not be a very stable configuration. Over here, you may say, well, this is as far apart from each other as the bonds can get. Everything here, all these bonds are 90 degrees apart from each other. But of course, molecules are three-dimensional structures. So even though all these bonds are 90 degrees, the bond between the carbon here and the hydrogen here and the hydrogen here, this bond angle, the angle between these two, is 180 degrees. And so they're not positioned as far apart as possible. It turns out, again, thinking in 3 dimensions, that the most stable position that these bonds can get, or as far apart as they can get from each other, is when it adopts a shape like you see down here on the bottom, where all of the bonds are 109.5 degrees apart from each other. Each of these 3 are expressing the same configuration, the same thing in 3 different ways. Here you can see the carbon bonded to the 4 hydrogens. The straight line here and here represent these hydrogens are in the same plane, or the plane of the screen. This wedge here for this hydrogen is kind of coming out towards you, and this hydrogen here are bonded with the dashed lines. That hydrogen is kind of going away from you. So you can kind of see it here in this ball and stick configuration a little bit better. So this is the most stable configuration for the bonds is in, as we'll see, this is it's called a tetrahedral configuration. So how is the molecular geometry determined according to the VSEPR model? We've kind of described the VSEPR model, but let's show you how to determine the shape of a molecule. And let's use water as an example. The first step is always going to be to draw the correct electron dot or Lewis structure for a molecule or polyatomic ion, whatever we're studying. So again, for water, if we were to draw the dot structure, of course, it would look like this. The next step is to count the number of electron domains on the central atom. So what is an electron domain? Well, the bonds and lone pairs around the central atom in a molecule are what we call electron domains. You may also hear electron domains called electron clouds, same thing. And the number of electron domains, sometimes you may hear that referred to as the steric number. So if an atom, a central atom has 5 electron domains, it has a steric number of 5. So that's a term you may encounter as well. An electron domain, one electron domain is a single bond around the central atom. A lone pair or electron pair on the central atom also counts as one electron domain. A double bond does not count as 2 electron domains. A double bond counts as 1 electron domain. And a triple bond, again, that doesn't count as 3 electron domains. That counts as 1 electron domain. And the reason for that is because, say, double bonds, the 2 bonds in a double bond, they're not able to move far apart from each other. They're always together in the same region. So because they're not able to position themselves further apart from one another, the bond angle, the double bond counts as 1 electron domain. Same thing with the triple bond. And remember, when we're talking about electron domains, we're only concerned with the bonds, lone pairs, the electron domains around the central atom or atoms for larger molecules. So let's take a look at water. For water, we have a single bond here, another single bond here. So we have 2 single bonds, and then we have 1, 2 lone pairs. So each of these, a single bond is 1 electron domain, so we have 1, 2, and then a lone pair also counts as 1 electron domain, so we have 3, 4. So water has 4 electron domains around the central atom. And the last step, after we've determined the electron domains, is determine the molecular geometry and the electron domain geometry from a table. Okay, so we need to look at a table and interpret that in order to figure out how to what our molecular geometry and electron domain geometry is. So we've thrown a new term in there. What is the electron domain geometry? The electron domain geometry is the geometry of a molecule taking into account all of the electron domains. So we count bonds and lone pairs around the central atom. Now, slightly different than that is the molecular geometry. The molecular geometry is the geometry of a molecule only taking into account the atoms that are bonded to the central atom. So we don't take into consideration the lone pairs. So the difference between electron domain geometry and molecular geometry is that one takes into account lone pairs and bonds. The other takes into account just the bonds. I'll give you an example of that in just a second. And if you have a molecule with no lone pairs around the central atom, only bonds, then the electron domain geometry and the molecular geometry are going to be the same. So remember, electron domains repel each other and they want to get as far apart from each other as possible. That's what gives us our molecular shape. Bonding pairs or bonds and lone pairs affect the shape slightly differently. Lone pairs cause the bonds to spread out slightly more than bonds do. So again, let's take a look at water. We said that, let's try to illustrate this using water. We have 4 electron domains, okay, and we have 2 bonds and 2 lone pairs. So let's remember that, and let's look at that table we mentioned. Okay, this table, first thing we want to do is figure out how many electron domains our molecule has. For water, we said that water has 4 electron domains, or a steric number of 4. So its electron domain geometry would be tetrahedral, okay? Because it has 4 electron domains, and anything with 4 electron domains is tetrahedral. So its electron domain geometry would be tetrahedral. Now, its molecular geometry, we look at, we don't count lone pairs and bonds the same when we're looking at our molecular geometry. Water has 2 bonds and 2 lone pairs. Here we have 2 bonds and 2 lone pairs. So we have 4 electron domains, 2 bonds and 2 lone pairs, and we say that a molecule like that has a bent molecular geometry. So the molecular geometry, we only look at the angle between the bonding atoms to give us our molecular geometry. So for water, it has an electron domain geometry of tetrahedral, okay, because we have 4 electron domains. We don't differentiate between bonding pairs and lone pairs here. We do with the molecular geometry. We only look at the bonds, and so water has 2 bonds, it has 2 lone pairs, and therefore has a bent molecular geometry. So let's practice determining the electron domain and molecular geometry for a few more molecules. If you would, pause the video and give it your best try and see if you can determine the molecular and electron domain geometries for the 3 molecules shown. Okay, so let's look at ammonia, NH3 first. First step is to draw the electron dot structure or Lewis structure. We can see that here. And then we need to determine the number of electron domains. Ammonia has 3 single bonds and a lone pair. Each of those is 1 electron domain, so ammonia has 4 electron domains. Then we need to look at our table. Our table, let's come here where we see 4 electron domains. If we have 4 electron domains, then our electron domain geometry is tetrahedral. We count all of those as if they were bonds, essentially. So here, with ammonia, 1, 2, 3, 4 electron domains, it's going to be a tetrahedral electron domain geometry. However, ammonia has 3 bonds and 1 lone pair, so its molecular geometry would be a trigonal pyramid or trigonal pyramidal, as you can see here. So ammonia's electron domain geometry is tetrahedral. Its molecular geometry is trigonal pyramidal, as you can see here. Carbon dioxide, let's take a look at it. First thing we draw is the electron dot or Lewis structure. Next, we count the electron domains. Again, just those around the central atom. Here we have 2 double bonds. A double bond, if you recall, each double bond counts as 1 electron domain. So carbon dioxide has 2 electron domains around the central atom. We're not worried about lone pairs on the oxygen because that's not our central atom. So 2 electron domains and no lone pairs. So let's take a look at our table. Electron domains 2, we find that here. So if you have 2 electron domains, your electron domain geometry is going to be linear, and your molecular geometry will also be linear. So carbon dioxide has a linear electron domain and molecular geometry. So the bond angle, or angle between these bonds here, is 180 degrees. They're linear across from each other. Let's look at sulfur dioxide. First thing, of course, we had to do was draw our correct dot structure. You can see that here. If we count our electron domains, the sulfur is our central atom. We have a double bond, that's 1 electron domain, a single bond, that's 2, and a lone pair, that would be 3. So we have 3 electron domains around our central sulfur. If we look on our table, we find 3 electron domains, and the electron domain geometry is going to be trigonal planar. So our electron domain geometry is trigonal planar, but it's not the same as the molecular geometry because we have a lone pair. Our molecular geometry would be bent because we have 2 bonding pairs and 1 lone pair. And so the actual bond angle is not 120 degrees, but slightly less, because that lone pair causes those bonds to bend slightly more than the ideal 120. So for sulfur dioxide, the electron domain geometry, as we said, was trigonal planar, and the molecular geometry would be bent. Again, we're just taking into account the bonding pairs and not the lone pairs. So if you would, here are several molecules, and for each of these, take some time and determine the electron domain geometry and the molecular geometry for each of these molecules or molecular ions. So practice those, and good luck.